All right. So when fuzzers miss, the no-hanging fruit. This is not an anti-fuzzing talk, but this is when you are fuzzing to be able to find exploits that are not easily found by EIP overwrites when you're pushing a fuzzer against a target. That's me, work for Tenable, part of SecureBit podcast, got a little exploit group. Sorry if you read my blog, I never posted anything, I hate writing stuff. Okay, so a little bit of definition on fuzzing. Fuzzing is typically defined as the automation and the exploitation discovery process. Basically, there's a few different techniques right there. There's expansion fuzzing to where you take a character, you expand it, put it into a buffer, you wait for it to overwrite EIP, or you wait for it to overwrite the heap manager, or hopefully overwrite data for a pointer. You get a little bit smarter inside of fuzzers to where you got something like FF as your integer, and it's the size of the payload that's coming after it. If it does a +1 to the integer, be able to wrap it, 0, you got a 0 size buffer you're pushing a bunch of stuff into. That's another exploit. You got brute force fuzzing, which is basically start at 0, 0, and you go all the way up through FF. You let it run as long as it can, and you can put it inside either a chunk or you can just run it raw. And it's a huge time to accuracy trade-off. It's extremely accurate, but it takes ridiculous amount of time to be able to run. And there's like listed commands where you got normal normal exploits that exist inside of it, like int wraps and normal values off int wraps. Can you stand a little closer to the mic? Yeah. Here, I'll actually. That better? Okay. All right. When I'm doing exploitation, usually the process I take is kind of laid out here. Get my app, know what it is. I usually read the protocol and different data, but the area that we're really concentrating in inside this talk is the discovery and the vulnerability to exploit method. And one of the keys is that second one that exists up there. So this is the vulnerability. It's as simple as it gets. It's just a gets call. Somebody doesn't know how to use the proper code. It's going to be local in this situation. This is easy as it gets. The code's on the bottom left. The stack frames are the code sets on the functions on the top left. And then that's what the stack looks like. Simple overwrite. Now you got the return address marking back to 41414141. That's as easy as it gets inside of exploitation. That's going to be what you get inside of fuzzers when you get that seg fault and the situations to where what you're looking for when you fuzz the target. And this is a talk to where the key is you're not going to get that. One of the things I have highlighted here is gets in kind of a pink color and red color. And this is really one of the keys behind this talk. Everybody looks at gets to be able to find where the exploit exists. Everybody looks for those str copies, mem copies. They look for the heap allocates to be able to find the buffer overflows or the heap overflows and different stuff like that. If you keep looking at that, you're never going to find the exploit. You're just going to find the vulnerability. The vulnerability or the exploit exists down there at ret or free or use after free. Those are where the exploits actually exist, and that's where the crash exists. All right, I got some demos I'm going to try and run through. There are 3 large demos, and the concepts of everything that I just brought up there is going to be what I'm going through in all those demos. Hoping to squeeze them in as quickly as I can. All right, pointer to lower functions. This is one I did a blog post on a little bit, so I'm going to go through it a little bit quicker, but it's a concept that's very important. So there's this graph right here, and this is a program that I'm going to be demoing. This is in the demo and the way that it works. So you got main calls start program goes into get login. If you put in the correct username and password, it goes down to login, returns back to from the program and closes out. If you put the incorrect username, it'll go back to get login. If you put the incorrect password, it'll go back to get login. It never exits from that method without being able to put in the proper data. The key in this is, if you see where the pink is, and I'm going to stay in this format the whole entire time, the pink is where fgets is, and you're pushing a 50 size buffer into a 25 size character set, and the exploits were ret. In order for this to be able to be successful, you have to be able to tear down the start program stack frame in order for ret to be able to hit where it needs to go. If you don't tear down that stack frame, you could fuzz those targets all day long with as many A's as you possibly want to push into it, and it's just going to sit there and run all day long, even though you are actually overflowing a buffer. And I'm going to actually go into the demo now. All right, still good? All right, so here's the code set on it. I've got main sitting here. I've just built a little bit of a buffer. Gives a place for people that want to do an exploit to be able to have place to put their ROP gadgets or put their shellcode if they want to do it on old style. And here's actually where start program is. This is where the overflow exists inside this area right here, and right here is where the exploit exists. If you don't get to that, you don't get an exploit, you don't get the capabilities. Now, it's very simple, username and password. You can type in all day long. Now let's fuzz the target a little bit. All right, right now, it's just shoving a large amount of data into. It's an expansion fuzzing. It's going to be fuzzing all the way up to 2,000 characters or 20, I can't remember, 20,000 characters. And this, I can guarantee you, is running a buffer overflow right now. On the actual target, it is overflowing a buffer, but there's no crash because the way that it's never returning back from the stack. Now, where the crash is going to exist is after you get to this process, if you log in, so successful, it's going to start tearing down the stack, and you're going to see here in a second, there's your crash. And I'm going to go actually inside of a debugger and show you guys. Can you guys see that fine, the debugger? All right, we're using a very simple just marker. It's usually not this easy because usually you're using standard N to be able to find the information. This is a local, just GCC compiled C program, so you can use easy buffers like fgets and printf to be able to find where the actual data is coming in. Following the data is really the most important part. Part of this is figuring out where it's going to. But in this situation, we get fgets in 2 different locations. Gonna throw a breakpoint on them. It's already inside the username breakpoint, so I'm gonna run past that real quick. All right, now we should be break on username. What you want to look at inside of this area is you want to look at where the data is actually existent. You don't want to look for the fact that fgets is here and the buffer overflow exists. You want to look for where the data is put to, so you can look for the overflow at that location. We can look at fgets right there on the bottom right is the buffer pointer to where it's going to be able to point to where it needs to go to. FD80, which is right here. We're going to mark off that. It's a pointer into the buffer. It's actually right here. And this is where the buffer exists and where it's actually storing the buffer. Now we look right down here and we see a return address that exists. This is our key point to where the exploit exists as opposed to where the vulnerability exists. And this is what we want to keep our eye on throughout the time when we're fuzzing, to be able to put log points at this point, to be able to look at the call stack, to look at different information that's affecting this address. Not the fact that it's putting a buffer in, but what's affecting this address that exists. Now by putting in the overflow is actually in the username. All right, you can see right here that it overwrote the return pointer. Really what you want to keep an eye on this is that whole entire concept of understanding where the exploit exists as opposed to where the vulnerability exists. I like taking this process by actually logging where my data is going, do unique strings to be able to figure out where it's at, and also you can hook into any debugger that you're using to log return addresses. That way you can keep track of what the return address throughout the whole entire process is. That's basically on that one. I went through that one rather quickly and a little bit simple because I got a post already online. You can read on it if you want. The second one's going to be a little bit more complicated in what the... All right, the second one's going to be on threads and stomping data. All right, basically a thread is a series of code that's running in a parallel process space in the same code set. So that means that two things are running at the same time using the same chunk of code without ever having to branch off into another process. So what's happening inside of a thread, the only thread that really matters to you is the main thread, or the only one that matters to the computer is the main thread, because that main thread's running. It doesn't matter how many threads it gets and how many threads crash inside that process. They're going to still keep running the main thread. All right, this is a little bit of a conglomerate mess of arrows, but what basically is going on is you got your main thread that's going on, and I branch it down into two to represent that there's two threads running at a certain point once the application starts. The main thread, as long as that's running in the left, in the left column, the program will keep running. So you run down the right path to actually run the application and do what you're doing. This would be an example of maybe you're logging into an FTP server or an SSH server. In order for like 30 people to be able to log in at the same time, you need to pop them out in their own threads to be able to keep them at the login process. Everybody's inside their own thread to be able to keep the login. It keeps it parallel. And if you're running through this process, you can see where you start at and authenticate and verify auth. And as long as you get down to the authenticate, which is where the start app's going to push you into, it's going to ask for the buffer. The buffer's going to put a developer mistyped a buffer size, put 200 byte buffer into a 20 size buffer, and the red ret is where the actual exploit exists. By taking that concept of where the red ret is, you need to look in the pathing to be able to find where you go above the ret. So we need to get back to start app successfully. This has got two different examples in one. I kind of combined them to be able to get the concept in and be able to fit all the examples in at the time. So let me actually. All right. So it's another very simple program. All it's doing is asking for a username and password to be able to log into the application. Bad username and password if you get it incorrect. If you log in, you just get a success. And I got it printing out the username and password to a buffer to standard out inside the space. You get the success. Now, we're going to do the same kind of thing to where we're going to fuzz the input. This is the 2,000 or 20,000, I can't remember what I put it to. Buffer size is fuzzing both fields at the exact same time. It's going to keep running through all the way up, and you're going to get no crash in this situation. I'm going to run through slowly on this one what all the situations are. All right, even if you log back in after that, still no crash. You did actually have an overflow. You had an overflow in the password fields, I think the correct one I put for this one. But it was unable to crash the thread because of the way the process runs. Now, going back to the slides. Okay, so we're running through the process space. And when the application starts, the start app is where it's actually loading up the function to be able to pull in for the username and password. That function that loads up is authenticate. That's the area where it's asking for the username and password to actually come in. When you actually put the username in, the buffer is stored in the authentication function block, which is the block in the stack that holds all of your local variables. When you put in the username and you put in the password, this is the password that actually the overflow is in, it's going to overwrite the return address from the authenticate function block. If If you overwrite the return address from the authentication function block, then you have to be able to return to that higher area to be able to get to it. Now, what's really killing on this and in threading is a thread doesn't ever have to exist except for that main thread. So when you fail login, all it's doing is going down to verify auth, and if you fail login, it just kills the thread. Goes back up, starts app again, goes back into the username and password. So you got the overflow to actually exist. It's on the stack. It overflowed the return address, but the whole entire time, all it's doing is just ending that thread every time, so it's just sitting in junk stack. Single time you get a thread too, you get a single stack that exists for just that thread, and because that thread's got its own stack, it can just get rid of it at any point in time. You can get a little bit of memory corruptions as far as memory leaks in this situation, to where if they're not cleaning up their buffers at the time when they do this, if they leave like a malloc and they never free that malloc at the point, then you can get constant memory leaks because you just keep putting whatever you want to into that buffer, and it'll run out the heap addresses until you end up filling up memory, whatever thousands and thousands of millions of characters that you have to be able to put in to do that. But in this situation, we're going to run through the example. All right. So if you're inside of a debugger and you ever see exit process or in thread, that's really the key point to where you want to make sure that that function's not running, and that's really where you're getting the key to where it's killing you on being able to find the exploit. So logging the fact that in thread did actually run, you will be able to find that exploit existing by making sure that you backstep from the pathing on that. I'm not sure if I explained that fully, but that's by understanding the in-thread runs and be able to like graph basically the pathing method on that, you can backstep where you're at to be able to figure out where the correct path exists. This is another example of being able to pay attention to what's going on and where the exploit exists as opposed to where the vulnerability exists, because if you look at the stack, it's very obvious that you get a 200 byte buffer and a 20 size buffer to overwrite the return address. All right, so let's actually run through it. So again, admin, DerbyCon, logs in, fine. Now, before I hit return on that, I'm going to explain a little bit of it. So this is the correct username and password, and this is where the second part of this that really comes in, is when you're overwriting onto a stack and the local variables, it pushes the variables in reverse order back onto the stack. So you got your stack chunks that go, or you got your stack frame, each one of those chunk out blocks to be able to push ESP up to be able to make local variables exist inside that area. If you overwrite a buffer overflow and a local variable that exists above a variable that's below it, you're overwriting that variable too. And if that variable is needed to be able to successfully exploit the program to be able to take a specific path, you can overwrite that variable anytime with anything you want. The key part on this that really usually gets people is the fact that null bytes exist inside of the end of strings. And that's what really terminates a string existence and to be able to read a string. In this example, we're using character compare as opposed to like str compare or something like that. But inside that null byte, you need to be able to splice it in some way to be able to get that exist in there in some way, or be able to sorry about that, be able to get that buffer to exist inside there. So what we're doing in the stack, let's see, make sure I'm in the right stack. What we're doing in the stack right here is we're pushing the username onto the stack, or the password onto the stack above where the username is to be able to give that, it needs to be able to authenticate through that, and it checks on the stack to be able to find that information. There's a little bit of a padding for, there's some balancing off the offsets, and there's a little bit of, there's two other local variables that get pushed in that area right there. And there's the offset size to the existence of the username that exists inside there to be able to authenticate. By putting that in a single string and seeing what data I'm actually stomping all over at that point, I could see that I need to have that existent by pathing where I need to go. So we got all the A's, all the B's where the where the overflow exists. Down in here, the return address would have been right about here. And you can see large buffer overwrite all the way down into like SEH handlers down here. So really you can go down into do a structure exception handler exploit down in this area. But if I run the program now, EIP equals 424242. Now you can fuzz this all day long, you'll never find it because it kills that thread all the time. It's all about taking that reverse engineer aspect and actually step into the debugger and see where your buffers exist and what's going on inside your buffers. All right. And one thing that can really get you on this is if they start a thread and they start a thread instead of a try-catch, sometimes the exception handler just says to end the thread. So if you're inside of a try-catch inside of a thread and you actually crash the thread, even in like a normal EIP override, and EIP tries to reference an address that doesn't exist, or it tries to reference 414.4141, then the exception handler is going to be able to pick up and say, okay, I'm going to kill that thread that exists. And you could do that in like a thread pool or whatever is going, or if it keeps track of the thread stack using multiple different methods, it can just kill out that thread. All right, this is the last demo. It's using exit and free. Exit's fairly obvious, but it's one of the things that's easily missed. When people are fuzzing an application, a lot of times what they hit is that initial buffer. They'll fuzz the buffer, they'll kill the application. They'll fuzz the buffer, they'll kill the application. They'll keep opening the application and keep hitting those buffers to be able to overflow that specific area without considering that someplace down the application method, it's actually going to call into that buffer, or it's going to be able to return a function stack later down the method. If you exit, it doesn't nicely all the time take down those function stacks. It'll sometimes just bring them out and you'll never get that seg fault. And even if you do get the seg fault in some situations, it'll just skip right past it and just crash out the whole application. The operating system will handle it. All right, so this is a very simple one. This is using heap instead of stack in this situation. So we just got main. It's a program that just echoes back whatever you say to it. And it's a command line, so you're going to open it up through the command line, put in a buffer into argv1, and then whatever you put in, it's going to echo it back to you. Now, it allocates space to be able to hold whatever you put in argv1, and it keeps it there for future use if it wants to use it. But the initial allocation is where the overflow exists. You can put as much as you want into that buffer, and it'll allocate over the heap. Now, this is a Windows 7-based system. This is as far as it gets into heap, and this is as far as the protection methods in heap. One of the key points in the protection methods with heap is not that the overflow is where it's being detected. Microsoft and many different other operating systems said that we're not going to detect the overflow, we're going to detect the exploit that exists. So all of the detection methods are on free or on use after free to be able to see that those exist and what's going on. So the fact that you overflowed, they're going to say, whatever, I don't care, you can overflow into another buffer, but as soon as I try to free a buffer or try to reuse a buffer is when you're going to get the crash. So it allocates on the buffer. We go into an echo loop down here to where it'll ask you if you want to do anything else. You keep running through that echo loop over and over again, and as long as you can stay inside the echo loop, you're never going to hit that heap free after the buffer from when it called into echo loop. If you don't ever hit free, or you don't ever hit that point to where it uses after free, then you're always going to exist inside of a loop that never does anything. And, Sorry, I'm getting this set up right here. Okay, now we're going to take the fuzzing method with this. This is not over network, so we're not going to take the normal socket type fuzzing method. What we're going to do is we're just going to do the standard in the way I've been doing the rest of them. This is just going to automate the process to be able to fuzz it by telling it to exit the program by saying no. I'll run through the program real quick so you guys can see what I'm talking about. You run in, it echoes back what you said to you. It says, would you like to echo anything else? If you hit no, it exits out. So all it's doing is automating the process. The new line returns is what's giving you the ability to fuzz, because that's equivalent to you hitting return, so it takes it as a return. All right, you can see we just fuzzed a large amount into buffer sizes. All it did was ever echo out. And you can see one thing that's key is only echoed out a specific size no matter how large of a data buffer that we put in. This is, I did have a little bit of wrapping to where it only allowed a specific character set because I'm a bad developer in this situation. I don't think that 30 and 40 matter in a difference. All right, so let's actually go into pathing and attach debugger. Oops, touching the wrong thing. Sorry, 1 second, I'm just getting the input on this. Should have been better prepared with this. Okay, I'm not going to waste your time making me try to figure out what that's at. I'm going to show you what exists inside of it. All right, inside of this is the source code for the application. One of the key features is that the way to exit out of this process without actually killing the process is to be able to type quit. This is something that the developer didn't log, or the fact that it wasn't initially meant to be in there, but he put it in for logging. This is actually very often something that you could find where a developer has undocumented function capability inside of an application that allow you to path to a situation. Now, down here in the echo loop, we'll ask you over and over again what you want to echo. It'll keep echoing out. Down here's main. This is where it calls into the echo loop, or it calls into echo. Echoes up here, it takes the argv1 that comes in through, the hell? Oh, that's the string. And then it does a heap create, puts that buffer inside the heap. Asks for your input there. As long as it's not no, it doesn't exit one, and then gets you in the exit loop. Now, by doing a little bit of reversing on the stack, or on the process, what you're going to be able to easily see is right here, while it does not say quit, it's not going to be able to exit that process thread. And what we're going to do is we need to actually utilize that undocumented method. So it's going to run in. Oh yeah, that's right. I put a little bit of a guard on it. So if you put too much, it's going to say stop trying to vol. Yeah. All right, so it echoes back the buffer. Now we're looking for the fact that this pathing, where do we exist inside the path at this specific point? We're at this point right here where it's asking us whether we want to continue down the buffer to be able to go into the echo loop. If we say no, it's never going to copy the buffer into the heap allocate area. If we say yes, it's going to copy that buffer into the heap allocate area, and it's going to send us into the loop. And this is where we would get in like IDA or something like that and look at the graph to be able to figure out what direction we're running into the buffer and where the buffer is actually allocated. All right, so we want to say yes to be able to take the correct method. I can keep echoing all day long here. I can fuzz this all day long. There is not actually an overflow inside this method, but as soon as I type quit, you can see we get our sig fault there because the pathing took down to the finally got to free, and because the exploit's actually inside of free, that's where we're going to get our exploit. Now, really inside this, the main concept that really needs to be taken from this is not the fact of these specific examples. It's more of a mindset that needs to be taken from it. And it's really this mindset right here. If you spend all day looking for where gets exists, you're going to spend all day looking for what a vulnerability exists. If you're an exploit developer, you're looking for exploits, you're going to constantly be looking at what exists to give you the capability to do an exploit. If you spend all day looking for gets and then figure out where gets buffer is a return, whether it's a pointer into another function stack, or if it's inexistent in the current function stack and it just never returns back from that, you can look at that return and be able to figure out where that exists inside of it. That's really the main concept and the main area to look at inside this talk is the fact to just keep that mindset when you're inside of things. Heap is one of the ones to where this can get fairly complicated, especially like a use after free or a like double free or something like that, because you need to be able to find a specific path to be able to hit farther down the application. If you fuzz all day long on that application, you're just going to be sitting there and hitting buffers that might be overflowing something, and use after free that may not actually be an overflow. It might be a use method. All right, and this is among many, many examples. There's really unlimited capabilities of giving examples of something like this. Logic is one that you're going to be able to see this happen a lot. You can't fuzz logic. You can try to automate the concept of a fuzzer to be able to understand what's going on inside of the application, but you can't fuzz logic to be able to figure out, well, if I do this, then the application just doesn't respond the correct way. And this doesn't even have to be an exploit in logic. It could be something as simple as if I just put .111, it lets me log in as admin. Pathing, that's one of the main things inside this too. If you don't take the correct path for the exploit, you'll never see the exploit. So understand where all your paths go and backstepping paths to be able to figure out where the buffers are coming from. You're going to get a concept way better on what's actually going on. Race conditions, binary protocols, variable overwrites, almost anything can exist inside this. It all matters on where you're going and where the exploit exists. All right. Now that you know all this, some of the ways that I take to be able to find these things and be able to find these situations is I really try to look at where the exploit exists, and then I send my buffers in. If I keep looking at where the vulnerability exists and I log maybe like if I log on gets or if I log on strcopy or if I log on whatever exists inside there, then I'm never going to actually see where the exploit exists. So I'll put a log or a break on all my returns, throw a buffer inside there. I like doing logs instead of breaks because if I do breaks, I got to sit there and constantly be hitting F2. If I put a log or a break on all my rets, I can sit there and let it run through. If I ever see any of my rets come back as my buffer, I know exactly where I'm existent. Log on freeze or log on heap allocates or log on anything that has to do with the heap and run through it to be able to figure out where the buffers are going to, figure out when I'm logging those, if I see a whole bunch of freeze and maybe 2 allocates, then I know I'm probably going to use it after freeze situation. All references to is a really good one that I use often. Ollie and Immunity both have this. And what it is, you can find the buffer where your data exists, right-click on it, and be able to go down to set all references to. It'll find every address that references that address that's a static address. If it pushes in a variable, it won't necessarily find that. But you can do all references to, go put breakpoints on that, figure out where the buffers we can copy it over, figure out where the stack frame is or where the allocation is. If there's already a patch for it, don't try to spend all day figuring out where the exploit exists. Go diff it, because you're going to be able to see exactly where it exists. If you're trying to recreate somebody else's work, you're working way too hard. All intermodule calls, figuring out where those weak functions are, where the vulnerabilities are. Just when you get to that point, don't worry about just setting a breakpoint on all of those. Worry about setting a breakpoint from the function stack that they're in on the return address or on the allocations that exist inside of it. Tracing sucks. You can spend all day tracing through something and never actually find what exists because you've got way too much data to come back. But it is one of those final methods. And really something like this isn't something to where you can just fuzz, get your exploit and then take the technique and learning ROP or egg hunting or something like that. It does take work to be able to figure out where these things exist. All right, any questions? Okay, so the first thing I do is read the documentation. Because if I just go directly in, even if it's something as stupid as I know the protocol like FTP, then I will make sure that I know the documentation on that product, because sometimes they're like, we added this super cool thing that exists. I'm going to hit that thing first. But in the process that you're talking about, I'll fuzz a target first just to see if I get the low-hanging fruit. If I don't get the low-hanging fruit inside that, I'm going to go in and look for specific spots that I know exist. If you try to step through code, you're going to be sitting there for like weeks. Even in small code sets, you're going to be sitting there for weeks trying to figure out where you're at and what's going on. So being able to look for specific data and specific types, throwing the brakes on rets to be able to figure out that's where my exploit is. It's in ret. So if I throw my brakes on ret and just throw a single buffer from the fuzzer in and just let it fuzz one specific thing, I can look at ret and just constantly keep hitting through ret and logging it back to another, like log out to a file or something like that. And I can see if it's ever overwritten. Really, a lot of the process, when I'm fuzzing even, I don't just throw a fuzzer at it and walk away and go start doing something else. My first run of my whole entire fuzz is a very large block that goes into it. I'll throw like a 20,000 character block inside of it, and I'll see where every single one of those go. Because sometimes the exploit exists at a block that's 10,000 size, but it doesn't exist in a 20,000 size because they're doing some kind of character set. So I'll look at where that buffer goes. If it doesn't ever go into someplace, then I'll step it down again and look where that buffer goes, and I'll try to figure out what function blocks I'm inside of. In stack-based exploitation, it's super simple. You got a bunch of blocks of exploitation. At the end of every one of those blocks, you got an exploit. And that's the way I see it. I got an exploit at the end of every one of them. EIP gets in control right there. All you got to do is just keep your eye on that location. And as long as you keep your eye on that location, you can figure out where the returns are. Now, this doesn't help you find things like pointer overwrites or something like that, but it's definitely going to help you find the normal stack-based overflows, or in some situations like the allocate or the free kind of exploits that exist. Did that answer your question? Anybody else?
You posted, is all this posted somewhere in your demo stuff, or is it we want to go off of it?
I'm going to post all the code. I'm going to post everything that's actually on here, all three of the demos, all the code. They're recording this, so you'll be able to see that online. And I'm going to have everything existent online. I don't know, I'll send it out someplace. It'll probably be on SecureBit's website. I'll probably post it up there. We got a wiki that's on there, so I'll probably throw it someplace down in there. I will make sure that everybody has absolutely anything, and I'll try to clean up my bad talking to make it a little bit better understandable in there. I'm much better at being able to review and have my wife review my speech before I actually talk. So, anybody else? All right, that's it for me. Thanks.